Okay, so in this lecture we will discuss Markov decision process. Please note that in our earlier lectures we discussed Markov chains and then we discussed Markov reward process. So once you are comfortable with my earlier lectures on Markov chain and Markov reward process, Markov decision process actually adds up one extra complexity into this Markov reward process. So what is that extra complexity? The extra complexity is the involvement of actions. So if you recall, in Markov chains we did not have any rewards or actions, whereas in Markov reward process we have rewards in our hand, and then basically Markov decision process is simply nothing but it's a Markov chain with rewards and actions both. So this is basically a very important concept and it lays the foundation for the reinforcement learning problems. So let us discuss Markov decision process in details and understand each and every aspect of it, so that once you go to the actual reinforcement learning problems, things will not become too difficult for you to understand. So let's start understanding the concept of Markov decision process. So what is Markov decision process? So Markov decision process, which are also abbreviated as MDP, is basically a finite MDP is basically a tuple which is defined by S, A, P, R and gamma. So by now you are comfortable with these variables which we discussed earlier also in case of Markov chains and Markov random Markov reward process, which is states, then we have the probability, then reward and the discount factor gamma. So we have already understood all these four parameters. So the last parameter which is further added, which makes Markov decision process different from Markov chain and Markov reward process, is actions. So let us discuss these actions, like what these actions are and how we are actually incorporating them in our Markov reward process. So this is basically, let's give a brief recall on each of these individual parameters. So S is nothing but it's a finite state of discrete time states, Sk, that belongs to the capital set S. Then A is basically a finite set of discrete time actions, At. So these are the discrete time actions which belongs to capital action A set. So if we have multiple actions, let us say A1, A2, A3 till A, let us say J. So all this will belong to the set state capital A. So all these are the elements of this capital state A. Then we have a transition probability, state transition probability. So now note that this time we have the state transition probability defined as this way: P S comma A comma S bar. Why we are doing that? Because actions are also involved. So somewhere actions will be in between the state transitions. So when you make a transition from state S to S prime, there will be an in between node which we will call as action. So that is also coming in between. So this transition, the state transition, will actually incorporate both the transition probabilities which are from state to action and then from action to S bar. We will discuss these details later, but this PSAS bar tries to capture this probabilistic distribution which involves from state to action, which you are taking as a probability, and from this action to S bar you are taking another probability. So the multiplication of these two probabilities are trying to be incorporated in this PSAS bar. If you note, in case of Markov reward process, there was no action involved and it was only PS comma S bar. So we were moving from S to S bar directly. So there was no internal internal node which we call as action. In our next slide we will discuss this, but this internal node is not there. So we have a direct S to S bar transition. So now the state transition probability is defined as this, which is nothing but the probability of agent moving to the next state S bar, provided it is in given state ST as S and has taken an action A. So let us see what this role of action A is in deciding these transitions, which agent is making from S to S prime. So before going there, let me tell you one thing. In case of Markov decision process, we are actually focusing on this distribution, this joint distribution, which is the probability joint distribution of next state and reward given the states and actions. So we have this as the joint distribution in our hand, which we are calling as the transition probability. Basically, we have this thing in our hands. If you look into Satan Barto reinforcement learning book, then you will find that they are defining this as the joint distribution, and from there you can actually get the other values of the transition probabilities out. We will discuss all of it in detail in our coming slides, but note that in case of Markov decision process, you have this as your transition probability defined. You can actually calculate this particular state transition probability by marginalizing over R here. We will discuss in details how you will get this from this. So if you see the definition for this joint distribution, it is nothing but the probability of S prime and R given state and action. Given your agent is in state S and has taken an action A in that state. So this is basically the definition for this particular transition probability. Let me make you understand like what this probability is all about and how we are interpreting the actions and the rewards in case of Markov decision process. So let us say you have a grid word example where all these states are defined by a tuple given by 0, 0, which is this state, and then we have the 2, 2, which is defined over here, and rest of them are quite evident by the convention that we are using for defining each of these states. So you can see 1, 1 corresponds to this state. Now we are having an agent which takes an action, and the action is in such a way that 70% of the time, if it takes an action up, then it will go here, and 20% of the time, if it takes the action up but it will go to the left, and 10% of the time when it takes an action up, it will be sliding over towards the right. So note, the important part is this is the probabilistic view onto the action. And what it is trying to say is that if agent is moving from here and it moves up, what happens is due to some slippery conditions, it will 70% of the time it will go up, but it might be the case that because of the slippery environment, it will slip towards the left by 20% probability and can slip towards the right with 10% probability. So chances are that it will slip to 20% on the left or to the right with 10%. And 70% of the time it will move up if it takes a decision of going up. So this is what is given over here. If you see, what I am trying to say is that agent is in state 0, 1, which is this state. And if it takes an action up, let us say this up action which is written over here, then there is a 70% chance that it will end up in state 1, 1, which is given over here. And the reward that is given to it is R equal to 1. So this particular probability is actually equal to 0.7. So this is what we mean by individual terms of this probability which we are defining over here. Similarly, in the second probability, what it is trying to say is that your agent is in state 0, 1. So it is in this state. It takes an action up. So it takes an action up. But what happens is because of the slippery environment, it slips towards the left side. So it slips towards the left side and it ends up at 0, 0 location. Reward given at that time of transition is given as 1, and the probability of this, that is the agent takes an action up, but because of the slippery condition it moves to the left, that value is given as 0.2. So that is the probability for that situation. And similarly you can go for the third one where the agent takes an action going up but it slips towards the right. The probability of that is 0.1. So in this way, I hope you understand all the individual terms of this joint distribution probability, that how we are actually interpreting this probability in the Markov decision process setting. Like in case of reward function in Markov reward process, similarly we have reward function in case of Markov decision process also. So here you can see we have these two definitions, and note, as it was in case of Markov reward process, we had two different scenarios of rewards. Similarly here also we have them, but the only difference is that A is also included now. So earlier A was not there because there were no actions involved in Markov reward process. So now in case of Markov decision process, we have actions. So actions will be added up here, as well as it will be added up at this point also. If you recall, this is similar to case of Markov reward process, where this corresponds to Rs and this corresponds to R of S comma S prime. So both these are different ways of expressing the rewards. And let me also give you the exact expression for how to evaluate the expectation operator on this and the expectation operator on this. And note that once we will discuss this, and once we will go through the Bellman equation for this Markov decision process, for the Bellman equation for Markov decision process starts from here. Actually, they do not start from this. If they start from this, then the different definition of RSA S prime will be used. So what happens is they are starting from this definition to derive the results. So that has to be kept in mind, and I will point it out later on once we will go to that slides, but keep this in mind. So now what we will do is we will actually derive the expressions for this as well as for this. So note, in case of Markov reward process, we had there was no action involved, so we had this particular probability in our hand. But now in case of Markov decision process, as actions are there, so now action will appear here. So this is the joint distribution that is available to you in the form of transition probability, and we can derive the individual transitions by marginalizing over this joint distribution. So here you can see we have the probability of going to S prime given S comma A, that is the transition probability the agent is making. We can get this value from this joint distribution by marginalizing over R. So here you can see if I marginalize over R, I will get this value. So that is important thing to be kept in mind. So basically this particular probability that you are getting over here is what I was telling you is basically a marginalization over the joint distribution which is given over here by summing it over R. So you will get this probability from this joint probability which is given over here. So now if we are interested in RSA, that is the first expression here, so we want to evaluate for this. So this is also easy. You can follow up from my earlier lecture on Markov reward process. Everything is same. So here you are calculating the expectation of RT given the ST minus 1 as S and AT minus 1 is equal to A. Note that this T is actually T plus 1 and this T minus 1 is T. So the expressions, if you write for these time indexes for T plus 1 and T, both these expressions will be same. This I have already clarified earlier. So this expression is actually equivalent to the expression, this expression given ST as S and AT as A, because the time index is changing. So now you can write this particular expectation which is given over here as this. And you can easily calculate this one which you have already done by marginalizing over S prime the joint distribution which is given to you. So once you have this expression, you can actually keep it over here and you get this expression. So this is the expression which is actually used in Bellman equation for deriving the results. And note that if you start with expectation given as a S prime, then you will get different expression for the Bellman equation. But here the Bellman equation actually starts with this, so we will end up with this expression. The second way of expressing the rewards, as I was telling you earlier, is SA comma S prime. So you can go about calculating this result which is given over here. So it's as simple as that. By seeing the expectation of reward, you can do it like this, you can write it like this, the expectation, and then you can use this particular expression which we are deriving from the very fundamental laws of probability which is given over here, which is nothing but the extension of the joint distribution P given A. So we are actually using this joint distribution expression and extend it to the conditional distribution. So you can use this particular expression by substituting these values. You will get this answer. It's very easy. From here you can get the value of PR SA S prime as this, and now you can actually substitute it back over here. to get the results for the expectation which is given like this. And note that in Bellman equation you do not find anything at the bottom, and the reason for that is you are not using this as the starting point for Bellman equation. You are using this as the starting point for Bellman equation. I will point it out later on once we will go to the derivation for Bellman equation, but you can easily recall from Markov reward process also that in Markov reward process we were actually doing expectation of R given S, and we were not doing expectation of R given S comma S prime. We were not doing that. So similarly here we are interested in expectation of R given S comma A and not S comma A comma S prime. We are not doing that. So that's why that's why the Bellman equation will not involve anything at the denominator. So if you notice, as we are discussing Markov decision process, we have actions actually which separates Markov decision process from Markov reward process. So these actions actually, somewhere, it will be, incorporated into another term which we call as policies. So let us understand what this policy is. So a policy is nothing but it's a distribution of actions for a particular given state. So policy is defined by this this symbol pi, and what it says is that for a particular state, what kind of actions you are taking in that state. So like for example, in the deterministic situation where, if you have like for example here, this is the deterministic environment. So here if you see, if you are in state A, we will be given that, once you are in state A, the action has to be going down. So that type of information is actually available in the policy function. So what it is saying is, if you are in state A, the action that will be given to it is down. So agent, once it reaches in state A, it will go down and it will reach to state D. So policy is basically defining a relationship between the action and the state in which it is. So deterministic policy means this particular probability that is going down in state A is actually 1. So this is the deterministic policy where you have the probability of going down in state A as 1. And and there is another type of policy which we call as stochastic policy. In that, what happens is, because of the stochastic policy, the environment also becomes stochastic. So here in this case, it is deterministic environment because of the policy that we are adopting, which is deterministic. So that's why the environment also becomes deterministic. In case of stochastic policy, environment also becomes stochastic. So what is there in the stochastic policy? In the stochastic policy, the actions in a particular state is probabilistic. So if you are in state B, then if you take an action down, then there is a 70% probability that it will go to state E, and there is a 10% probability that it will go to state A, and 20% probability that it will go to state C. So basically, there is a probability distribution for a given state in which you are looking for different, there is a probability distribution of actions in a given state. So this is the diagram to show that. Here you can see, if you are in state B and if you take an action down, then with 70% probability you will end up in state C. Similarly, if you are in state B and you take the action right, then based on this action, there is a 20% probability that you will end up in state E. And if you have taken an action left, then there is a 10% probability that you will end up in state A, given this action is taken as left. So all these things are actually, giving you a kind of distribution, like in a state, what kind of action what is the probability that you will take that action to reach to some other state. So for example, let me say it again. So if you have a state, let us say here S, and you take a action something like this. So actions are basically represented by a dot. So this is important in terms of the backup diagram, which we will discuss next. So states are represented by circles, actions are represented by dots. So if you take different actions, let us say A1 here, A2 here, and A3 here, so depending upon the probability, you will end up in different states. So for example, if you have a probability distribution here, which is actually, I am drawing in terms of the histogram. So if it is 0.2, then you will end up in some other state, which is like, let me draw it again here. So right now this is actually, 2. I'll just bring it down here. So once you take so this is there, so there is a probability distribution. So here you have, let us say, taking the action A2 as 0.7, and this one is basically taking an action as 0.1. So based on the actions, based on the probability, you will take different actions from this state. So once you take the action A1, A2 or A3, depending upon this probability distribution, you will end up in different states. So that can be some other state like this, S prime. And based on this action, you will end up in some other state, let us say S double prime. And based on this action, you will end up in some other state, let us say S triple prime. So in backup diagrams, you will see something like this, where you have small dots represented by actions and bigger circles represented by the states. And so these are the futuristic states, and this is the present state in which we are working on. And this is the probability distribution corresponding to the stochastic policy. And in case of deterministic policy, what will happen? In case of deterministic policy, a specific action will be having a probability of 1. So this thing will all be 0, let us say, and you will have this action as 1. So all other branches will go away. So this branch will go away and this branch will go away if I take action A2 only with the probability 1. So that this is what is represented over here in mathematical form. That is, you are actually, in a given state, you are taking an action. What is that probability? If it is 1, then it's a deterministic policy, and corresponding the environment will be also deterministic. And if it's a distribution of the probability in a given state, then it will be a stochastic policy, and the corresponding environment will also be stochastic. So this is what we are trying to show over here also. So you can see these small dots corresponds to the action, and the intermediate arrows actually represents this particular function, which is being in state S, you are taking an action A1. So it's represented by this policy function pi, and you end up in state A1. You take this path A1, then in this you take an action A2, so you will follow this path. Similarly for all the other actions if you have for a given state. So this is basically the concept of policy. So policies are also of two types. One is the categorical policy, which I have just discussed here. So the stochastic policies are all categorical policies where you have discrete actions available, and for each discrete action you have some probability corresponding to that. So this is what is shown over here. So if you have for example, if you have a grid environment where agent is moving in that environment, and it can take multiple actions of going up, left, down, or right. So with each of these actions that the agent will take, the corresponding probabilities related to that action will be given over here. So you can see that these distribution of the probability, based on this you can have different actions. So all this is the probability. So there is another type of policy which we call as Gaussian policy, which we will discuss later on, but for now you can understand that this is basically the Gaussian curve that we have over here, and the states are actually continuous. So for example, here the speed of the car is the state in which that car is. So you can see that depending upon the speed we have different states. So this is a clear-cut example of a Markov decision process where states are continuous. So here as you can see over here, we have an optimal speed of 100, and we are trying to be at the center of this Gaussian, which is the mean, and that is 100, and we want to be as close as to it, to this 100. And if we try to deflect from this ideal speed of 100, so what we are trying to do is we are trying to go away from this mean speed. And what we are trying to do here is like we are trying to explore different states. If you have a wider Gaussian, so you are trying to actually go away from this particular ideal action that you are taking, that is at this particular speed you are trying to take this optimal action, right? So but if the Gaussian curve is steep, like for example, if the variance of this Gaussian curve is very steep like this, then then in this particular situation, what happens is the actions that you will take for a specific speed is rather limited, and the exploitation is more as compared to the exploration. So we will discuss this exploitation and exploration concept in the coming slides. But what it means in short is that if you are exploiting something, it means you are actually using the already existing knowledge that you have gained for a particular event. And like for example, if you are going to a restaurant and if you have already tasted a food which looks delicious to you and which tastes delicious to you, so you will try to order that same food again in that particular restaurant, and you will not take the risk of going for some other alternative. So that is basically exploitation of the knowledge. But if you try to take a risk and try to opt for some other dishes which are available in the restaurant which you have never tasted earlier, if you are taking that risk, that it means you are actually exploring the environment. So that is basically exploring and exploitation. And our agents are basically doing similar type of activity when they are moving in the dynamic environment. So they try to explore and exploit at the same time, and they try to find out the optimal balance in between the two. This is basically the axis, which is the probability axis. So somewhere it is not, it has to be the probability of taking an action being in a state st, and the speed of the car is state. So when I am saying exploitation, when I'm saying exploitation means you are actually looking into a very peak narrow curve. So in a particular state, selecting the action is high, and it drops down. The probability drops down as you move away from this state. So it clearly indicates that if you are in this particular state, the probability of taking that action is exactly or close to 1. Whereas for the other states, it drastically reduces as you slightly move away from this ideal state, that is that particular speed of the car. Whereas in this case, which is a wider Gaussian curve, here you still have the probability of being into other states here with different probability scores. You still have value which is not close to 0. So in that sense, in this particular thing still allows to explore different states, whereas this Gaussian curve actually exploits to be in state 100 only, and other states or other speed of the cars will have a close to 0 probability because of the sharp peak in the Gaussian curve. So Gaussian policies are used to formulate the continuous Markov decision problems. So this is basically again trying to explain the concept. Thank you.